This is a quick review of the interpolation lecture. Interpolation is a process we use in GIS to estimate values at unsampled points because of time or money. We can't estimate everything, so we sample things and use those samples to help us estimate or predict the values at unsampled locations. There's several different sampling techniques you want to be aware of. The systematic sample, the random sample, the cluster sample, or the adaptive sample. All of these samples have advantages and disadvantages. The systematic sample is fairly easy to understand, but it could have biases. For example, there could be a ridge running down at this location. We just happen to select the top of that ridge, so we would have a very biased sample. But it's fairly easy to understand. Random sample is a very little bias or least biased system, but it's very difficult to actually find the locations. And it does nothing to oversample at the areas where there's lots of change. Cluster sample minimizes travel time, so you would travel to an area, and then when you're there, you would do quite a number of sampling based on some rules. Adaptive sample requires 2 stages. You need to have some sort of pre-knowledge of the area so that you can select more here and less where there's less change. So it's quite a efficient sampling method, but it requires prior knowledge, so it often is more costly and more involved. Now, once we've sampled, we take that information and we use that in an interpolation method, and there's many different methods. No one is absolutely best in all situations, and the accuracy has to be judged by withholding sample points. So we'd sample 1,000 points, we'd put 100 aside, and we'd use those at the end afterwards to validate our estimation or our interpolation process. The interpolation generally creates a raster surface, though there are some exceptions, contours and Thiessen polygons, for example. This is our sample base that we'll be using. The first one that you want to know about is the Thiessen polygons. This is often used for rain gauges. It's quite simple. It's referred to as the nearest neighbor. And the Thiessen, the basic idea with the Thiessen polygon is you start with the sample locations and you put a frame around it, and then you put connecting lines between the sample locations, temporary connecting lines that you'll erase later. Then you find the centers of those connecting lines and erasing the connecting lines, and then you start by using those center points to create bisectors that divide the area. So that this being the sample point, everything around it, until I get close to the nearby point, gets the value of that center point. So it's a nearest neighbor. So here's an example of it. Here's your points. Put a box around it. Put your temporary lines between the nearest points. Bisect those points, bisect those lines, create the perpendiculars through those bisectors, and then connect them so that you would have this particular point here, and gets every area around, all the area around it gets the value of that point until you get near the next point. So here's the Thiessen polygon. Another one that's quite commonly used, easy to understand, is the fixed radius, where you're taking your particular data points, in this case 6 and 8, and you're throwing a circle of some predefined radius, and that's the key in this interpolation, is how it's the radius of the circle. You throw the radius onto your point layer, and you'd sum or aggregate or average, in most cases, the values inside that, and send that to the appropriate raster cell. So you would pass this circle across the entire area, averaging as you move along. So the 6 and the 8 are averaged to 7, the 9, the 3, the 6 are averaged to the 6, the 5 is averaged to 5, the 15 and 5 is averaged to 10. So it's fairly simple to understand, but it's dependent on the radius of that circle. And here's an example of a fixed radius on our sample. The other method that we need to talk about is inverse distance, where we're estimating the unknown points, giving weight or more weight to the nearby points. And the further away points have less weight in our equation. So the important thing to understand is as we're summing, we're trying to identify our z values. Those are the known location. And we're trying to find our unknown. So we're taking our known locations over the distance between the known location and over the inverse distance. So here's the example of that. We've got an unknown location we're trying to estimate and 3 known points. And we have the difference. The distance to this is 4, this is 6, this is 2. So we're taking 50, which is the known point, over its distance, 30 over its distance, which is 2, 52 over its distance, which is 6, okay? And we're solving that over the inverse of the distance, 1 over 4, 1 over 2, 1 over 6, okay? And we're then estimating that interpolated point to be 34. And the weight, obviously, is coming from the 30. Now, in this inverse distance, an important part of it is whether you square the distance or not. And that's giving more weight to the nearby points. The other thing is the actual number of points, the I, and that is how many points you use in your estimation. So there's an exponent, and there's the number of samples. And here is where we're using 6. In my example before, I was using 3. In this, we're using the 6 nearest in linear. We're not squaring anything. In this case, we're doing the same data, but we're using the 6 nearest, and we're squaring the distance. So we're giving more weight to the nearby points. Here, we're squaring it, and we're using 12 points. So in the formula, you have the big choice issues are the I, the number of points you're using, and the exponent to the distance. Okay. Another one that is that we want to talk about is a trend surface, where it's a statistical model where we're forcing our interpolation through between the particular lines. So it's a surface where a statistical fit model where we're trying to fit lines between our points. All right, estimating those coefficients through a regression model. So a trend surface looks like that. Another one is a spline. The difference between a spline and a trend surface is that in the spline, we're actually forcing our equation to go through the points rather than using a regression to find the best line in between them. Okay. Another one is Kriging, which is similar to inverse distance, and that is where we're using a statistical process to help us as well as the distance. And it relies on this idea of autocorrelation. And that is, as I move on this axis, okay, there's a corresponding movement on the y-axis. So as I move to 800 here, this is moving up. So as I move to 1,000 here, I'm moving somewhere close to 1,000 here. So there's a tight correlation between moving on the x and moving on the y. In this case, there's no correlation. As I move on the x, I could be all over the place on the y. So Kriging is building on the idea that sometimes data is autocorrelated, and you use that to better estimate. And in the process of Kriging, the key starting point is this idea of lag distance. So the first thing you do in Kriging is you would take the points. These are points. I'm not doing anything about the sample points, my estimated points at this time. I'm just dealing with my sample points, and I measure the distance between all my sample points. And this distance I'm putting together into a lag distance. Excuse me. So I measure the distance between all my points, and I put those distance measurements into buckets, and that I would treat. Say that if I'm measuring a point, one measurement is a foot, another is a foot and a half, another is a foot and 3/4, another is a foot and 7/8. I could put that all together in 1 foot buckets, based on some sort of lag distance. And it's important you're understanding this lag distance, and that the idea of lag tolerance is how big the bucket is, right? So I'm estimating, I'm taking my values, and I'm going through a process of measuring the distance between them, and I'm putting these H's into buckets, and I'm not and I'm grouping those buckets, and so you get the same sort of idea as a bandwidth, where you're putting together information, similar values that are close together. And so an important parameter in this is the lag distance and corresponding lag tolerance. So then after you've got these buckets, all right, you go through this, you look what's in that bucket, and you establish the semivariance, or how similar those points are within those buckets. And you would then calculate this semivariance, you'd calculate that semivariance for each of the lag distances. And you end up with something called a variogram. So for every of those lag distances, say for the 1 bucket, for the 2, for the 3, for the 4, for the 5, you calculate how variable they are. Are they tightly correlated, or are they very loosely correlated? How the variability. And this is an idealized environment. Okay, so you then calculate this with your estimation. With your buckets, you would take each bucket, the lag distance, figure out the semivariance, and you would create this curve. Then you would take that and you would apply that to your data to actually estimate your unknown points. And this is an example of that, where we have our model, okay, and then we start throwing our data into it. And you can see that early on, the data here is quite tightly autocorrelated. But where we have wide distances between our points, we start to lose the correlation, and the ability of the model to predict up here is not as good. Okay, so there's several different models. We talked about Thiessen, inverse distance, and spline, where they're exact interpolators. So where you sample, okay, and then your interpolation is going to get the same result at those points. Whereas the non-exact, the Kriging, the trend, or the fixed radius, they're actually either doing an average, or they're doing a regression, or they're using statistical process, as in Kriging, to estimate those values. So at your sample points, you might not get exactly your sample value. The predicted and sampled might vary a tiny bit. This is an example of our sampling, systematic random cluster. And we then go through our various different methods, and you can see they look quite different. If you see something like this, this is obviously a nearest neighbor, whereas if you're looking at a trend surface, you're starting to see these smooth lines, a little bit like a spline. It's a little more difficult to estimate some of these, or guess what some of these other shapes are, though the inverse distance often has this sort of bullseye look, especially when you're squaring it. Or taking it to the third power. Okay. An important part of the interpolation is validating or checking your work. It's very common in interpolation to subset your samples. You would divide your sample up. Say you sampled 10,000 locations of air quality. You would take 500 or some number of them, and you would split it out at the beginning, the very beginning, and you would take those 500 and you would put it aside. You'd put it in a drawer. You wouldn't do anything with it initially, and you'd take the rest of it, the other 9,500, and you would take those points and you would use that to create your model. And then and then after you're all done, you would take that sample, that subset, that training data set and the test data set. You would take the test to validate your information. So there's two types of validation you do. One is you interpolate your values from your samples, and then you compare your interpolated value to your sample, okay, within your training data set, okay? Then you also compare your predicted value to the actual measured value of that set-aside data set. So there's two types of checking. One is this basic validation of your points against the outside value, the value that you withheld and you didn't use in the model, the training set. And the other is the actual model itself, is to compare where you measured and then what you predicted. So it's important you have some sort of validation process to say, I interpolated this data and my root mean square of my error is 48 meters. And my standard error is 75 meters. So that there's the types of measurement, validation, and accuracy assessment. Another thing that we want to talk about is core area or home range, and this is very commonly used with wildlife, where we're using sample points where we've collected information about a wolf or some animal, or sample locations from some GPS collars. And we're using that to estimate where the animal is most of the time, where their home range is. And there's different ways to do this. We can use this core area. We can use a mean circle where we would take the X and Y, and we would average the X and Y location to find the center, okay? And so we would find the center of the spatial locations. And then we would use the distance to all the points from that center to create an average, what the average circle is, all right? And we would, this would be the mean of the average from the center to all these points. And then there'd be obviously the standard deviation or the maximum distance circle. So that we average the X and Y points to find the center, and then we average that center point to the distance to create this mean circle. Another way would be to take the observed animal locations and create either a convex hull or a concave hull. The convex hull is a 980 degree outside dimension. This is less than 180 degree. The concave here, or the convex. The convex is far more common. Another one is to actually use a density function, where we're looking at our particular sample points, and we're saying within a certain bandwidth, okay, within a type of bandwidth that we establish in our density function, and that bandwidth could be 1 foot, could be an acre, could be a hectare, some sort of bandwidth, and within that bandwidth, we process our data, and we create a density function for each of those, that bandwidth, each group that's within that bandwidth. And then we sum those, we put them on top of each other to create a concatenated or aggregated density function. And it would look roughly like this. The sample points are our sample points, and we create a narrow bandwidth, a medium bandwidth, or a wide bandwidth. So in the narrow bandwidth, you can see that the density function is aggregated. We're saying this is the most dense area. Out here is less, and it isn't very dense out here, obviously. If our bandwidth is wider, we've got much richer area. So there's pluses and minuses, but the idea is that it's using a kernel mapping, and the key is that a density function based on some sort of established bandwidth. And so you create the density function, aggregate the density functions, and create your surface.